The change in enthalpy as the reactants form elements is shown here as delta SDH. Simple decomposition is what SD stands for. The change in enthalpy as the elements form different compound products is shown here as delta FH, F meaning formation. The change in enthalpy for the entire reaction is shown here as delta RH, R for reaction. It is the net difference between the two enthalpy changes. A positive value is indicated in this potential energy diagram, and it shows the overall reaction is requiring more energy than it releases, and is considered therefore an endothermic reaction. The communication of enthalpy changes can be as an enthalpy of simple decomposition, hence the subscripted SD, or combustion for the subscripted C, formation for F. Generally, the subscripted R is sufficient for any reaction. The temperature and pressure of the surroundings will affect the overall enthalpy change of a system undergoing the chemical reaction. Therefore, it is important to keep these things constant. The superscripted degree sign indicates SATP conditions. The units for these enthalpies of reaction are in kilojoules, and as mentioned before, if the enthalpy change of a system is exothermic, the sign we apply to account for the enthalpy change will be negative, and positive for an endothermic change. To communicate molar enthalpies, we write it in the exact same way. It is worth mentioning that while the McGraw-Hill textbook does not adequately differentiate between the symbols for change in enthalpy and change in molar enthalpy, some other texts use a subscripted M following the H to specify the symbol for a change in molar enthalpy. Sometimes the McGraw-Hill text even omits all subscripted lettering. It is obviously a convention that has not yet been solidified. In this course, I will use the subscripted M notation, although it is important to note that this subscripted M will not appear in your unit exams or final exams. At the end of the day, the important thing to remember is that the units for molar enthalpy is kilojoules per mole, and is typically the correct way to differentiate the difference between the molar enthalpy values and just enthalpy values. So when you see a delta H, pay attention to the units and its context, enthalpy change or molar enthalpy change. Communicating enthalpies. One way to represent enthalpies is by way of a thermochemical equation. In the example given here, we have a balanced equation showing the combustion of methane. Included is the enthalpy change for this reaction as the reactants form products. Since the combustion of methane is exothermic and releases heat to the surroundings, as most combustion reactions are prone to do, the expression of this released energy is communicated as a product in our thermochemical equation. We wrote a similar equation for cellular respiration, showing energy as a product because it was produced in this exothermic reaction. The endothermic reaction for the formation of nitrogen monoxide is shown here, indicating that energy is required for the reaction, and so it is expressed in the thermochemical equation as a reactant. Again, we did a similar thing before for photosynthesis. Energy from the sun is required for this reaction to proceed, and so is included in the equation on the reactant side. Delta H notation. Delta H notation shows the enthalpy term written as a separate expression beside the chemical equation. These are the same equations written in delta H notation. Since the enthalpy expression is not part of the equation, to indicate whether or not the reaction is endothermic or exothermic, we resort once again to the positive and negative signs. While it might be obvious a combustion reaction is an exothermic reaction, by convention we make sure to include the proper sign when using delta H notation. This is the thermochemical equation of methane again. The change in enthalpy for the combustion of methane is negative 802.5 kilojoules. This is the same equation, only this time I doubled up the amounts. Instead of 1 mole of methane, I now have 2. Instead of 2 moles of oxygen, I have 4, and so on. Notice the change in enthalpy for the reaction. Since I doubled the quantities of all the components in the equation, it makes sense to double the change in enthalpy. After all, if I were burning methane gas, twice the amount of methane would produce twice the amount of energy. Each component in the equation contributes to the change in enthalpy. For instance, 1 mole of methane in this equation produces an enthalpy change of negative 802.5 kilojoules. 2 moles of oxygen in this equation produces negative 802.5 kilojoules. 2 moles of water vapor produces negative 802.5 kilojoules in this equation. I keep saying in this equation because these substances in a different context are going to produce different changes in enthalpy. For example, 1 mole of methane in this equation, a simple decomposition reaction, has an enthalpy change of positive 74.6 kilojoules.